Thanks. Okay, so before we start, I wanted to make a few more comments about the angular velocity ordered angles we found last time. So this is what we found. Angular velocity of generic frame R with respect to another generic frame A, and we started calling this R as rigid body, just thinking about something physical moving in space. Given the rotation sequence 3, 2, 1, and writing the omega in the R fixed coordinate system, literally 1, 2, and 3, this is what you will get. Sine of phi plus theta dot cosine of phi, this is a dot here, E2, and finally you have psi dot cosine of theta cosine of phi minus theta dot sine of phi. And as you can imagine, by looking at me holding these notes, don't memorize this, it's no point, I don't want you to. Now I underline that we express this vector. This is a vector in the end. Like every other vector, we just chose to write it in the basis which is fixed in R, which is the object or frame that we're looking at, which is rotating with respect to A. You are more than welcome to write these in the basis which is fixed with A if you like. There's nothing wrong with that. The reasons behind doing it this way, it's because, as I mentioned to you, in reality, you have sensors that can measure angular rates, and they are usually bolted to whatever it is that you are observing. So a spacecraft has a gyroscope, which is going to actually give you numbers for these three values. So it's going to be attached in a very specific way to the body frame of your spacecraft. You know exactly along which axis is measuring, and it will give you three numbers that are in a body, in an R fixed coordinate system. So that's why it's usually expressed this way. And the comment I want to make about singularity is the following. Let me rewrite these the following way. I can write component by component omega 1 Ra, omega 2 Ra, omega 3 Ra as the following. Allow me to call this column vector if you like. This is not a vector again, it's three numbers. Just put one below the other in a matrix form, right? That's what I want to do. So if on this other end I have the three derivatives of the angles, psi dot, theta dot, and phi dot, and you start populating this matrix here, okay, let's see what you get. That's easy. So omega 1 is this, omega 2 is this component, omega 3 is this component. So I start from this. I see a phi dot, so I definitely have a 1 down here. I don't see any theta dot, so I have a 0 here. And then I see a minus sine of theta here. And likewise, you do the other term. Psi dot has a cosine of theta, sine of phi, cosine of phi for theta dot, 0 for phi dot, and then the last one is cosine of theta, cosine of phi, minus sine of phi, and another 0. Why do I write it this way? Because actually, the most common thing that you will see, especially if you go into spacecraft dynamics or aircraft dynamics, this is usually solved in terms of the angles, derivatives. So you would get an expression which gives you psi dot, theta dot, phi dot as a function, another matrix that multiplies these three, which again, these are the three numbers that you will get from a sensor in reality. You're not going to do any hardware work here, but this is just to give you an idea of what people do with this. And then if you have this information of the angular velocity components, you can integrate numerically these three angles. They are derivatives. I don't know how many of you have taken numerical integration classes on computational algorithms, but that's what it's done. You can numerically integrate those three, given that you know the initial values of the angles, which means you know the initial orientation of the body R with respect to A, and then your sensor is measuring what's going on, and you can integrate the angles, which means you give the time history of how the object is moving in space. always thinking in terms of what would be the case with the particle. You give me the velocities, I integrate the velocity given the initial position, and I can tell you the trajectory of the particle, right? If you give me x dot, y dot, z dot, if you're using Cartesian coordinates. Now, if you look at this and you really want to invert that expression, which I'm not going to do at all, but if you really want to do it, the first step is, for example, compute the determinant of that matrix, right? If you want to do it that way. And this is not a math class, so I'm assuming that you know how to do it. What I do, I start from the top left element, start counting signs, plus, minus, plus. This is a good one, because if I go down this way, I only see a number here and then a bunch of zeros. So I start from here, plus 1 that multiplies the determinant of this smaller matrix. So the determinant of that matrix, I don't know, let's call it A. Call this A. Well, actually, let me call it B, just because I've used A for the frame. If we compute it, it's what it is, minus cosine of theta sine squared of phi minus cosine of theta cosine squared of phi, which means minus cosine of theta, right? So when you invert this matrix, what you will have to do, you will have to do other things, but you will have to divide everything by the determinant of the matrix, if you remember how that's done, which again is not part of this class. But this cosine of theta will be, so there will be something up here, minus cosine of theta will be denominator of your calculations to invert this matrix, right? And now you see, mathematically speaking, also what is the issue with singularities. If the second angle goes at 90 degrees, which is theta, not only, physically speaking, is not a good representation of your orientation, because you may have infinite combinations of the first and last angle that still give you the same orientation, so that's a bad thing to have. You also mathematically have the issue of having a 0 down here, right? Which, if you actually do numerical integration, it will not stop MATLAB from keep going, almost never, because you never really exactly get a 0. But substantially, this is wrong. It's mathematically wrong. It's physically a wrong choice of representation of attitude if the second angle for the 3, 2, 1 sequence goes to 90 degrees. If it doesn't get close to 90 degrees, as we said, like for an airplane, then you're fine. You just want to stay away. And some of you ask me, what happens if you get close? Well, if your theta angle at some point during your maneuver over the airplane or whatever it is that you're looking at gets to something like this, 88.9, 89 point something. Well, you're close enough, you switch representation, as we said last time. Don't do 3, 2, 1, do 1, 2, 1, something else.
We can multiply with some other factor and divide with other factor.
There is nothing you can do mathematically that will solve this issue. If you're using a 3, 2, 1 sequence, that's a sequence I choose. And the second rotation goes at 90 degrees. The first and last axis will be aligned with each other, and you're done. You can't use it.
I'm saying we get phi dot, theta dot, and xi dot. So
yes.
These are the three values which
Yeah.
we get, and then we take this
Yeah.
like at the inverse. So I'm saying we take another thing, like something else, and then take another factor and then multiply, divide with that factor. Then we have 4 factors, and then we change the values of the set 4th factor.
So you're talking about quaternions now, which is not what we're doing. So is that the point? So representing orientation with more than 3 parameters.
No, I was just thinking maybe I multiply something so that the 0 also.
Oh, no. There's nothing. You know, always do this. Represent in your mind what happens. You do a first rotation psi, and then you get to this intermediate axis. Then the second one is 90 degrees, and then this axis here goes down, exactly pointing in the opposite direction with respect to your original one. And so the last rotation is going to be parallel with the first. So this means that you can pick infinite combinations of these two that represent the same final orientation. That is wrong. Because again, it's like saying that you don't have a unique way to represent the position of a particle once you picked your coordinate system. And why would you pick a coordinate system that has not unique representation for what it is that you are observing? It would be crazy. It's like you give your address to someone and that address keeps changing, and then people are trying to find you, but you keep changing the address, right? Doesn't make any sense. But again, if you stay away from 90 degrees, you're fine. So there is also a mathematical reason why 90 degrees is not a good thing to do. And the alternative to quaternions are I'm sorry, to other angles are quaternions, which are actually used, especially in spacecraft attitude mechanics, but we're not going to do them here. They have no physical meaning. There's no angles that you can really visualize, but they don't have the singularity problem. And also, they get rid of sines, cosines, and all those weird functions that we don't like. They're much easier, but okay, that's a topic for another class. Are we solving problems at this point by yourself from the book? Okay. So today, we really have 2 more lectures about kinematics. I'm going to do intrinsic coordinates today and an example with them, and then we'll do rolling and sliding next time between rigid bodies, which is a very important topic, and then we start with kinetics. Okay? So today we have intrinsic coordinates. And there is a reason why we're going through the pain of defining all these different types of coordinate systems. It's because when we start solving kinetics problems, you really want to be able to switch between coordinate systems and use the ones that are more convenient for you. Because in that case, you really have to stick with one coordinate system only. So you want to choose the one that is more convenient, as we will see. Anyways, intrinsic coordinates. Assumptions. We have a given reference frame A and the coordinate system fixed in A. So this is point O fixed in A. And point P, which is moving with respect to A, and this is its trajectory. Trajectory of P, so at this point, this will be the velocity of P here, V of P in A, with respect to A. Of course, the trajectory is also dependent on the reference frame. With respect to an observer fixed in A. Do we all agree that the trajectory depends on the observer? Why does it depend on the observer? How would you explain that? This line.
Any point along that line will have a different position depending on the...
Right, right. So, yeah, I'm looking at this point from O. I measure where it is. This is not working. I measure where it is from O. So, of course, it depends on my, depends from my point of view. So we'll call R its position. This is 3D Euclidean space. R is the position of P with respect to the point O. And we want to define a very special type of coordinate system, which is called intrinsic. Intrinsic has a specific meaning. If you look it up, one of them is belonging to the essential nature of something. So we're going to define a coordinate system that would not even exist if there wasn't any motion. So this is a coordinate system that will go with P. We'll have an origin P, and one axis will be the velocity direction, and then we'll define 2 other axes that are perpendicular to the velocity. And the first assumption is, well, there's a lot of assumptions here. I am in a reference frame A. I've defined the coordinate system. I'm looking at the point P. I can measure its distance from O. Another assumption is that V of P in A is basically never 0. There must be motion. So that's why it's called intrinsic. This exists if, so the nature of this something that we're looking at now, this something now is motion of a particle. If there is no motion, there is no intrinsic coordinate system. And so what we dealt with so far are coordinate systems that are called, in general, Cartesian, spherical, cylindrical. What are those called? What would you call them? This is intrinsic. Those are extrinsics. It's extrinsic coordinate system, like this one here. So if this is a basis, classical big EX, big Y, big Z, this coordinate system does not care what P is doing. It's there, I've defined it. It doesn't matter what P is doing. P can disappear, can explode, whatever. I don't care. It's still there. The one that I'm going to define instead, so it's outside the motion. I observe things from extrinsic coordinate systems. I measure things from outside the motion. The one that I'm going to define is actually, it only exists if there is motion. It really goes with the motion. And we'll define when it's used once we're done. But we use it all the time. OK, so I don't need this anymore. Let's define the let ET, first basis, first unit vector of the basis, be defined as V of P in A over its magnitude. I just define it that way. Did I call the point P, P, A, P? Well, I dropped the P here. I think you don't have. After all, there is only one point, so we can just say this is V in A, which I can also write as V in A over, if you want to use just another letter that represents the magnitude of the vector, you can do this. Anyway, this is obviously a unit vector which is going in the same direction of the velocity of P. So you can start right away making the observation, well, if there is no motion with respect to A, this goes to 0. Even worse, the denominator goes to 0. This coordinate system doesn't exist at all, doesn't make any sense. OK, then we define E, what did I call this? En, I think it's called, or EB. No, En, this is En. I need to define two other vectors that need to be obviously in the plane perpendicular to the velocity if I want a right-handed orthonormal basis. OK, En. And I'm going to do it this way. I'm going to say that this is defined by d dt in A of Et, the one I just defined, the tangential. So this is called tangential unit vector. So obviously tangential to the trajectory like V is. OK, ddt in A of Et over its magnitude. I always want unit vectors, so always normalize what I have. Now, question for you. I'm telling you this is perpendicular to this. Why is that the case? Except the norm here. This is a scalar, right? I'm telling you that d et dt in A, I'm claiming this is perpendicular to Et. How do you prove that? I can't just come up with something and say, oh, this is perpendicular. Okay, from what do you start here? From which property do you start to demonstrate this? How do you start this demonstration? Say that I'm asking you this. You need to prove this, prove this. Where do you start from? I've heard dot product of what? Right, this is what we've done, right? Right at the beginning when we were defining angular velocity. Dot product of Et with itself, it's a unit vector, it's 1. This is a scalar. I can take the derivative of this in any frame. I do it in A, for example, d et dt dotted with Et. This is commutative, so we ended up having 2 equals 0. So this means that these two guys are perpendicular to each other. You need to be able to show these things to yourself before you move on. OK, so that's fine. That is a vector which is perpendicular to unit vector perpendicular to Et. Good. And then last one, well, guess what? OK, this is called principal unit normal to the trajectory. Tangential unit vector to the trajectory, of course, here you may want to add. And it's good to add it just because, again, this trajectory depends on A. And this is expressed by the fact that these are all derivatives taken in A. And if you like, just to be thorough here, since we said we never skip these steps, this is d dt in A of r over its magnitude, right? Which then we say it's equal to this. It's v in A over the magnitude of v in A. Okay, principal unit normal to the trajectory, and then the last one, which we call EB, it's En cross with ET. Just take the other two and do a cross product. And this is the principal unit binormal to the trajectory of P in A. I'm not writing everything I say, but when I talk about trajectory, it should be obvious that that is dependent on the reference frame. So it is the trajectory of that point. There's only one point moving here, and it's with respect to the reference frame, A.
By this, we are allowing the coordinate frame at P to rotate about ET.
I'm not sure I got the question. So some.
Yeah, we define En as a differentiation of ET over the magnitude.
Yeah.
So in that case, and we have just defined this. So in that case, only the vector P ET is fixed, and the other two can.
There's nothing fixed here. This point. Okay. First of all, the fact that I'm talking about a trajectory, it means that there is an observer looking at the motion of P from A. So imagine yourself in A. You're looking at P moving. If P is moving along this trajectory, nothing is fixed. I mean, this trajectory can be a sinusoidal wave, can be whatever you want. So ET in this moment is like this, in this other moment is like this. It does, nothing is fixed.
Yeah, so En and EB can rotate also. Like it's this, it's just, we are just...
ET is the direction of the velocity vector. The other two are very well defined directions. I mean, if you, we'll do an example in a second, but once you define ET, the direction of its derivative with respect to A, it's a very well defined direction. It's computed by that formula. By that rate of change. So you could take En and EB and rotate them by an arbitrary angle about ET if you like. That works too. But do you see my point? So once you have ET, right, defined, which is the direction of the velocity vector, then you take its rate of change and normalize it, and that gives you some direction, which is En, and then you have your EB.
Yeah, what I'm saying is in the ET plane.
I'm sorry, EB in this case is going in, of course.
In the ET plane, En and EB can be anything.
En and EB can be anything. If you have another way to define two unit vectors and 90 degrees with respect to each other that are in the plane perpendicular to ET, that's also a fine intrinsic coordinate system. But first of all, if you don't define these, well, I start here from defining ET as something that has to do with the trajectory itself. There is the velocity of P in A, which defines ET. So I see the fact that this is intrinsic to the trajectory by the fact that I've used VA. Okay. Then I go here. If I completely forget about ET and I just pick any direction perpendicular to ET, it doesn't sound intrinsic anymore. There are concepts like curvature and other things that we're not going to define that really need you to define the normal to the trajectory that way. If you are in a plane, for example, I don't think we need this anymore. If you are constraining your trajectory to a plane, usually what happens is that you see ET, for example, in this point here, in this direction, and then the normal is probably like this. And it's very useful because it can allow you to define, that is needed in kinetics. it can allow you to define forces that are going this well. If you can do it the other way, it's fine, but you can change the sign. That's the most I would do. But picking an arbitrary vector, for example, in this case, for En, that is, I don't know, 45 degrees pointing down from the board. Why? Why would you do that? To make your life harder? So those are definitely using the characteristics of the trajectory. This VA will change, and so I define ET as something that has to do with VA, and then En also has to do with VA because it's the rate of change of ET, and then EB also has to do with the trajectory because I started from VA and I never left VA, basically. Yeah, but you can, yeah. It's just not done that way. Nothing special, right? If there is no motion, though, this doesn't exist. Doesn't make any sense. When do you use these type of coordinate systems? What do you think? Let's see what problem I have here. When would you use them? Anyone has taken any classes on aircraft flight dynamics? You have, right? Drag force is opposite to the velocity. So that's probably a case where you actually are using the intrinsic coordinate system. You don't know, but you are. You project all your forces in the direction, in the two directions of the velocity and perpendicular to the velocity, and also the binormal, which is your side forces on the airplane, right? So drag will be opposite to the velocity, lift is perpendicular, and the other direction is side forces. That's when it's used. Anything moving on a track, which is what we're going to do here in an example, if you're moving, I don't know, if you're on a roller coaster, that will be probably a good idea to use those types of coordinates. They probably use them to design roller coasters. I don't know. I could ask someone. I would say that they probably do that. So, okay, let's do this example here. Little ex, little ey, this is already depicted for you, actually. Okay, so there is a point moving on a circle, and this is supposed to be a circle. I know, terrible. I promise I will not draw the problems for the exam by hands. Okay, so this is a point P moving, it's constrained to move on a track, which in this case is a circle. And let's see, what are you given here? You're given this drawing here, this angle from big Ex is called theta. And then I'm telling you that the distance OP is R, is a scalar. This is the length of this magnitude of this vector is sine of theta. Okay? And also I'm giving you that theta dot is positive. Okay, I want to find Vp in A. I have to tell you what A is. Probably the acceleration is not that important. And I want to define the intrinsic coordinate system. Okay, same story here. Defining reference frames. This is basically done for you. A is the reference frame of the board where Ex and Ey are fixed and the origin is in O. Well, I'm giving it to you, so there's really no need to do that. Then, now you could, of course, take R projected in Ex, Ey, and take the derivatives. I don't think it's a good idea, so let's define another reference frame here. I'm going to define a reference frame which is rotating, which is basically as these following 3 points, for example, as O as 1 point, P as 1 point, and then you can pick, you need to pick a third point, right, to define a reference frame, non-collinear points. So which one would you pick? I picked O and P. I want to define a reference frame that goes with the motion. So one way is picking 3 points, OP, and I need another one which needs to be non-collinear with those two.
Intersection with EY?
I'm sorry, intersection with?
EY. When the theta is 90.
This point, but then this triangle has to go, it's fine. This triangle has to move with theta, right? It's a reference frame. Or another way, that's fine. Or another way to say this is, well, you take A and you basically allow it to rotate about this axis here, which is, I guess this is EZ, right? We don't need it, but this is EZ. Anyways, I can do that. I can define a reference frame that goes with theta, which is basically A rotating about EZ. You take the board and you allow it to rotate. So in that reference frame, I can define the usual E, R, E, Z, E, theta coordinate system where, and I'm calling this, let's call this B. So in the reference frame B, I have origin. Well, I want to say the origin as O is fine for both, right? And then I have little er, which is along, what is it called? OP. EZ out of page. And E theta is the cross product. Why am I doing this? Well, someone is giving me this function for r, so I really want to use it. If r is evolving as the sine of the angle theta, it's probably easier for me to write r like this. You can also write it as sine of theta times cosine of theta, which would be the projection on the x-axis. Do we see that? If sine of theta is the magnitude of r, and I want to use these components here, this one and this one, you can. But then you have sine theta cosine of theta, and here you have a sine squared of theta, which is fine. It's just a little sines and cosines, and when you start taking derivatives, as we've seen, it's not probably very convenient. So if someone is giving you something like this, the expression of the magnitude of the vector already, you probably want to define, again, you don't have to, but there should be an alarm that triggers and say, maybe I should define a unit vector along the direction of r. And that's your r. So, but then if that's my r, when I want to compute the velocity of p in A, and I'm going to drop the p because there's only p here, v in A is d dt in A of r, but r is expressed in a coordinate system fixed to B. So transport theorem, these will never go away, plus, I can write an r here, omega b A cross with r. Okay, so this is, what is it? Let's do it. What is the first term? Theta dot cosine of theta, little er, plus theta dot Ez, that's the angular velocity, cross with sine of theta, little e r, which is equal to, what is Ez cross with er? Okay, so I have theta dot cosine of theta, little er, plus theta dot sine of theta, e theta. And let's try to do the acceleration too, just for fun. So that's it. That's the velocity of p. Acceleration of p in A is d dt in A of the velocity of p in A. But guess what? This is written in a coordinate system which is fixed in B. So I do the same. d dt in B of v in A plus omega BA cross with VA. Okay. Derivative of that. Then now we start having a little bit of fun. What is the derivative of this vector in B? The rate of change of that vector in B. theta dot double dot. What do? I need to take the derivative. Theta double dot cosine of theta minus theta dot squared sine of theta ER. Are these steps clear? I mean, I'm assuming that these derivatives are clear, right? Theta is the function of time here.
Yeah, can you just explain how we could pair out sine theta for B in A, for omega B in A?
This? No. This is omega. As a cross product. So this is omega BA cross with R. Make sense?
Yeah.
Okay. So I'm assuming these derivatives are okay. You know how to derive functions that are composed by, that are functions of functions. That's what I'm doing here. So plus theta double dot. So I do the derivative of the first times the second plus the derivative of the second times the first. That's what I'm doing here. Making sense? That's the VA dt in respect to B. And then I have omega is the same, theta dot little ez cross with V. Theta dot cosine of theta ER plus theta dot sine of theta E theta. Okay. I'm not really going to need that, but let's finish it. If you think about it, the way I described the intrinsic coordinate doesn't really use acceleration, so I don't really need it. I can stop at velocity and go from there. But let's finish this. Okay. What do we see there? This is still the acceleration of P in A. Okay. Let's leave this as it is. Theta double dot cosine of theta minus theta dot squared sine of theta ER plus, we know this, theta double dot sine of theta plus theta dot squared cosine of theta E theta. Is everything okay? Cross products, easy with ER. I erased that, so I don't want to make mistakes here, like I've done a couple times. I'm going to draw this here. This is Z, right? What do I have? EZ cross with ER, so E theta, and I see a theta dot squared cosine of theta E theta. That's the first one, and then I have, I'm assuming this is a small dot here that you cannot see, but it must be. Otherwise, it doesn't make any sense dimensionally. EZ cross with E theta is minus ER, so I have a minus theta dot squared sine theta ER. Agree? Disagree? Good. So collect all these. I only see components along theta and ER. Of course, why would things appear on EZ? Everything is on a plane. These are all good checks. If you're doing this and you start seeing EZs floating around, but your original problem was planar, something is wrong. Something happened. Okay, so common factors here. What is common? This is common with ER, so I have theta double dot cosine of theta. Twice that, right? I think we've seen these formulas before in other problems. Very similar, right? That's it. And then another 2 there. Okay. This is a 2 here. E theta. Okay, fine. Who cares? I don't need the acceleration, but we've done it. Okay, that was a nice exercise. Now let's do the intrinsic coordinates. V, I need it. I need this velocity. I want to write it up here. I'll just copy it up here. Theta dot cosine of theta little er plus theta dot sine of theta little e theta. Okay. ET. VA over its magnitude. Can you do it in one step? If I look at that vector, what is the magnitude of this vector? Theta dot. So if I divide everything by theta dot, is cosine of theta ER plus sine of theta E theta. Okay? Now think about this. We'll do the calculations, but it's good to give some thinking to a problem before digging into calculations. So if this is ET, do I expect its rate of change d et dt in A, this that I'm going to calculate next? I'll write it up here. Do you expect this to have components out of the plane? So ER and E theta are in the same plane of the board. EZ, big EZ and little EZ were sticking out, but everything is happening in the plane. So this is little ET, this is little ET. It's moving, it's doing something, but it's always in that plane. Why would its rate of change have any component on the Z direction? I don't expect that to happen, right? It shouldn't. Nothing is happening out of the plane. If everything is happening in a thin piece of paper and I am looking at the paper from the side, I don't see anything going on. I don't see anything happening on the Z direction. So that tells me that En that I'm going to compute using this is probably going to be in the same plane. And so EB sub B, oh, it cannot be 0. No zeros. I need a coordinate system. I need always 3.
EB would just be in terms of EZ.
It will be Z. It will actually be Z. It must be Z. If ET and I've just commented that probably En that comes from this calculation are on the same plane, EB can only be Z or minus EZ maybe, but can only be in that direction. So I know what I should expect. And now I do it. I want to do it because it's better to check if it's plus EZ or minus EZ and what this is. I want to write it in terms of sines and cosines of theta, etc. But I know more or less what to expect, right? So, okay, so En, we know it's d dt in A of Et over its norm yes.
Shouldn't E t be in the direction of E theta?
No.
Because this comes out to be in the form of E.
No. The point is moving on a circle, right? I removed the drawing here. So this is the problem. I know that this is moving in a circle, and of course my circles gets worse and worse. The velocity is tangential to the circle, right? I only know that this is given as a function of theta, but that's okay. But I do expect the velocity to be in the direction of tangent to the circle, while E theta is perpendicular to R, so they're not exactly the same vector. If they can be, they are up here, right?
So ET, En, I mean, these guys don't really have a fixed direction, right? They just move along.
They are intrinsic to the motion. They are stuck with wherever the particle is going. Et is following the velocity vector, and En is the rate of change normalized of that unit vector. Yes, and that's a good question though. Yeah. So the way I just defined, because it's convenient for me, ER to be along the radius and E theta to be this way. They don't have anything to do with the velocity vector, right? I'm using them to express the. So I basically use this coordinate system to express the intrinsic coordinate system. But this is done. If you are an observer in A, down here, you're looking at the motion of this object, you may be able to measure R and theta, right? But then you may need, if that's an airplane, for example, you may actually need to be able to write ET, EN, and EB. It may be convenient for you to project drag forces, lift forces, whatever it is that you're looking at. So this is not just a waste of calculations. They are actually used, even if you need to define them with respect to another coordinate system. Because of course the trajectory that you're looking at exists because you are looking at the point moving from a reference frame A, and you've defined a coordinate system in A. So of course your intrinsic coordinates will be expressed in another coordinate. There's nothing else you can do. But they are useful. So let me do d dt in A of ET. How do I do that? 5 minutes. I should be able to do it. Now ET is expressed in a reference frame, in a coordinate system, fixed in a reference frame, which is not A, it's B, right? So I can do the transport theorem on this as well. Why not? B plus omega B A cross with ET. So this will give me, okay, theta minus theta dot cosine of theta ER plus theta dot cosine of theta E theta plus, now this is omega, theta dot little z cross with ET cross with that vector sine of theta E theta. Making sense? Oh, yes, thank you. Thanks. Okay, let's do it. Let's do, well, let me write it here. Continue here. That is a minus theta dot sine of theta ER plus theta dot cosine of theta E theta. Can you do those for me quick? EZ cross with ER.
E theta.
E theta. EZ cross with E theta. Minus ER. So in the end I get, is everything okay? EZ cross with E theta. Yes.
For the first number.
They don't go away, no. It's a minus 2, right? First and last. Make sense? Okay? I have the feeling we have an error somewhere. I don't know why. But I kind of get the feeling that there may be a minus missing somewhere. No. Yeah, that's right. Okay. I just don't like it. That's fine. That's another problem. Okay, so I need to do the norm of that. What is the norm of that thing?
Just two theta.
No, it's not too bad, actually. Yeah, that's right. I didn't see that there is a common term. Okay, well, that's bad. Not too bad. Okay, so yeah, that was the part that I didn't like. So if this is the numerator, remember, En is d dt in A over its norm. Same thing. So if that's the vector that is on top and the norm is 2 theta dot, well then this is, what is it, minus sine of theta ER plus cosine of theta E theta, right? Okay. And then cross product. Let's see if EB is actually coming out of the page. EB is En cross with ET. So it's...
So the book defines it the other way. And if I just did En cross ET and you get negative ET. Yeah.
Okay.
So I think the book defines it as ET cross En.
Oh, EB? Yeah.
Yeah.
What did I say?
When you wrote it on the border.
Yeah, it's
you
ET. I'm
wrote
sorry.
En cross with ET.
Yep, made a mistake. Thank you. Yep, it's ET cross with En. Yeah, the order is, is ET, EN, EB. They go in the order I defined them, and I did the cross product wrong. So, yep. ET cross with EN gives you EB. Yep, thank you. Okay, so if you do it, I don't know if we have time to finish this. Cross ER plus cosine of theta e theta. Well, you can finish it yourself at this point, but it seems pretty obvious to me. I have all cross products between R and theta. It will be something on EZ. And actually get EZ. You can do it yourself. There will be a sine squared and cosine squared that will basically add up to 1, and you get EZ. Okay? Thanks.